Parametric design is the next chapter in the world of design. But how does it fit into your work? How does it fit into your daily life as a designer and in the projects that you're working? What I hope you'll see as you go through the Serpentine wall tutorial and look at this is to have a design theory behind your work. So as you also think about fabrication and how to develop your systems and your code, that you'll be thinking about why it's valuable and why does it work as a design method. Life is very complex. We live in complex biological and physical systems, from crystals to ecosystems, even to our very own internal organs. But design is about simplifying these complex problems into very simple variables that we can tackle. Complex problems for much of our existence have been solved by very simple methods, and pretty much it's limited our ability to really address them. But parametric design gives us the ability to do something different. Our design now can be a much bigger solution to complex problems. Whereas before, we of course have very great solutions, especially in fields like architecture, where we're dealing with how the sun works, how structural systems work, and maybe an earthquake zone. But if we look at systems such as in nature, this nautilus shell to our left, we start to see how nature has pretty much derived this system that expands in a very systematic way. The solution is this system in the shell. And to the right, we look at a system that we've solved with a typical house, but the parametric allows us to be a lot more like the left than the right. And both have their place, but parametric starts to give us a comprehensive way of solving these more complex problems with a very good complex solution. So now, what are we looking at when we start to think about complex systems? Well, design in general has been this set of solving problems with a convention and with a plan to work that convention, such as how we use 4 walls and a roof for a house. But if we start to look at it as a system, not just the points and lines and geometry, which is also very great, but we start to say, what if we start applying patterns, such as the Fibonacci sequence to the right? And what if we start to look at different systems and how we could maybe use solar panels, or how we could use a material connection? Our systematic understanding forces us to make things work at a very elementary level, and it starts to give us new possibilities in design. Let's look at the example that we have here, a very top-down solution of a bicycle, where we have a very recognized convention: wheels, frame, handlebars, the pedals. This is very much a determined system. It's from the top down. But to the right, we look at a truncated icosahedron, where we pretty much can say we're starting the system that expands, and we have our triangular parts that are part of the whole. But the idea is we have like this very consistent network of points and lines that if we say we're going to change the thickness of our lines, or we're going to change how one pentagram works or one hexagon works, it could be done across the entire system. And that lets us lead into this very great logic that we can develop from parametric systems. It's the material logic. The unit component, such as a geometry that's very simple, that we expand and cover a surface with, will be still coherent as we arrive at larger systems. To the left, as we are talking about sails, it's very important because this fish scale is a system that's spread across the fish, and it has this material logic that works as the fish can move and sway. But yet the individual unit is still something that works. So if we start to break that down into our design in the right from my thesis project, where a unit component is spread across a surface that is responding to different stimuli, pretty much it's like an agent system. Each of the unit components is intelligent. And so as they're all intelligent, but they work together, the material logic keeps them consistent. And the parametric plus in this situation is that we can solve a problem that's the size of a house or a small wall or even a car to an entire tower. By working on that unit component and putting together those systems, it works at the small scale and at the larger scale. And so here's some examples from nature that I want you to look at because you can see the benefit. This is a spider web that we can see that is pretty much the home for the spider, but yet over in a much larger system, over a tree and multiple trees, it's still consistent. It doesn't fall apart. And so one of the things that we can start seeing with parametrics is how we can solve larger problems, how we can look at more complex solutions to those, and we can address them with what we have. We don't have to build a new set of tools and conventions, but we can really solve them at a base level and expand it to larger systems. And here's another nature example, is us looking at how we can examine nature for how nature looks at expansion and larger problems, and how does a flower expand. It's using a very simple system, but we can look at it and observe it using geometry, using ways to examine how is it working with the sun, how do the materials work. Nature's a tool, but also form itself is a tool. As you can see from Shigeru Ban's project, to the left, the Hermes building, to the right of looking at fractals, how fractal systems can be derived at a very small level, and as they grow larger, they start to create a form. So we both can learn from what nature is doing to see the benefits of parametrics, but we can also just start deriving systems and take the same understandings that the component that's consistent can expand, it can grow. One of the things that I would hope you also to learn is that as we have this coherent system, that we are developing not just the big system by itself or the small system, which is obviously tempting to say, I'll develop this really small thing to work, but we start to figure out how they can both work together. And as we looked at how they can be compiled and assembled, such as our parts, our connections, we actually have a much stronger way to design. So as you develop in parametrics, whether using Grasshopper or Rhino or whatever programs are out there, that you're always thinking about how we could come back from both scales, how we could start to think about the built world as well as the theory world, how our lines work and how our little systems work. You'll have a much stronger system, and we'll see how parametrics is that next system. That design can encapsulate and solve problems in a much better way. And I hope you'll see that in the Serpentine wall as going back and forth between how the detail can work, as you can see from the right, of how each part of it, the slats to the rail, can work on a larger scale, and how we could start to incorporate difference and change in a system so that it's consistent across all parts of the design. The form and the structure, the form and the material, they all become seamless as the design system is not just about I'll make a set of structures and put a material on top, but they're all thought about in one complete system. And so in parametric design, we actually can, of course, think about just the material surface of parametrics, but it could be a complete parametric system. And it's depending on how much you're willing to develop in this, but the fact that parametric has such strong potential really puts it as something on the table, not just for this project, but any project that you would like to work on. So as you look at the Serpentine wall and look at the process at which I put it together and how you can script it, I hope you also be thinking about these design theories, how we can go between the material scale and the prototype scale, going from a very consistent unit system to a larger framework in the material, in the form. And I've also included some references as you develop in your parametric work that you can look for and look into how they've worked on parametrics and parametric ideas. John Fraser is really great, Fry Otto, Paul Coates, also Laura Spurbeck, Klaus Osterhau, Jesse Reiser, and of course Zaha Hadid, the Fano Science Center, which really before a lot of the parametric work that she's done and that has been happening at her firm. But also, if you look at Greg Lynn, he's been working with parametric forms for over decades. And so as you look at the type of possibilities you have with parametrics, I hope you'll see some opportunities, maybe some ideas you can bring forward as you work in your projects, that you'll see that parametrics is not just another technique, but it actually is a process version to the next wave of how we design. It has more potential than just a simple new way of designing parts, but it actually can inform the way we entirely design and how we create new solutions for an ever-changing world.